video, I'm going to be recording solutions to the 2024 VCAA Exam 2. This is actually the second time I've recorded this video because I recorded it earlier today with no sound. So hopefully it means I'll get all the answers correct first time around, but let's see how we go. Or either that, I'll be a bit fed up about it and I'll skip some steps, but let's see how we go. Okay, so question 1, the asymptotes of the graph of y equals log e of x plus 1 minus 3 are. Okay, so a log graph only has a vertical asymptote, so we can definitely rule out the y equals asymptotes. A log graph looks something like this. This one has gone to the left by 1, so that asymptote is going to be at x equals -1. Yes, it's also gone down, but that doesn't change where the asymptote is. So x equals -1 will be the asymptote. Obviously, you can use your CAS to sketch it. Just clear the CAS. We'll get to those answers later. Obviously, you can use your CAS to sketch it to see where the asymptote is, but really it's more efficient not to need to. So it's there as a backup, but you shouldn't really need it to be able to find that asymptote. The other thing, rather than a graphical process, is an understanding of the fact that the thing inside a log has to be positive. So x plus 1 has to be bigger than 0, which is why the asymptote is at x equals -1. And why the domain is x greater than -1, and that means the asymptote is at x equals -1. Okay, question 2. A function g has the derivative. Given that g of 0 is 5, calculate the value of g of 2. Okay, so we're going to need to work out g of x before we can work out g of 2. So obviously g of x is going to be the antiderivative of the derivative. So that means we're going to get x to the 4 on 4 minus x squared on 2 plus c. So the g of 0 equals 5 is about finding c. So 0 minus 0 plus 5, sorry, plus c equals 5. And so that means c equals 5. And so therefore g of x is x to the 4 on 4 minus x squared on 2 plus 5. And then working out g of 2, 2 to the 4 is 16, divided by 4 is 4. 2 squared is 4, divided by 2 is 2, plus 5. So that's 2 plus 4, which is 7. And so option D. So obviously, again, you can use your CAS to help you there, to help you work out that antiderivative. But the process of what, to help you substitute 2 into that expression and evaluate it, but the process of what needs to be done still needs to be thought through by you. And by the time you then type in the steps into your calculator, it's actually quicker to do it by hand. Obviously, it's a tool, and if your algebra is not very strong, then by all means go ahead and use it. But we're looking for efficiencies in working through the multiple choice questions. You only really have half an hour to spend on the multiple choice, given the amount of marks they're worth, and they can really take a lot of time. Okay, so a discrete random variable x is defined using the probability distribution below, where k is a positive real number. Find the probability x is less than 4, given that x is greater than 1. Now, when I did this earlier, I added these up, 5, 10, 15k, equals 1, so it tells us that k equals 1/15. But actually, when you see how this works, we don't actually need to know the value of k to be able to answer this question. So if we're finding the probability that x is less than 4, given that x is greater than 1, that's the probability of x being less than 4 and greater than 1. So therefore, that is x between 1 and 4, not inclusive, over the probability x is greater than 1. So that is probability that x equals 2 plus the probability that x equals 3 over probability that x equals 2 plus probability that x equals 3 plus the probability that x equals 4. So because there's going to be k in everything, the k's are going to cancel out anyway, so you actually don't need to find what k is. So probability x equals 2 and 3, so we're adding those together for the numerator, so that's 8k, and then we're adding those 3 together for the denominator, so that's 10k, so that gives us 8 over 10, which is 4/5, so option C. Okay, question 4. If the integral of f of x from b to a is -5 and the integral from a to c is 3, then so b is between a and c. Okay, so this, I usually like to think about these things graphically. Now, I usually draw it doesn't really matter the level of accuracy of the graph that you draw, because the logic still holds. So my initial thinking here is, okay, we've got 3 unknown values, a and b and c. we know that the integral, they're not necessarily equidistant. Let me change that just so it's misleading. They might be, but they might not be. So the information that we're given is that the integral from a to b is -5. Now this is where my diagram is not at all accurate, because obviously if that integral is -5, that's an area that's below the x-axis, but the maths of it still works. Just it's sort of easier to draw it this way. We know that the integral from a to c, so that yellow bit, is 3. And so therefore the integral from b to c is going to be the yellow minus the shade of black. And so that's going to be, this bit here is going to be 3 minus -5, and so it's going to be 8. Now obviously we could draw a more accurate diagram about that, but it would still give us the same information. So what we essentially have happening here is that obviously the area between a and b is below the x-axis, or at least the majority of it's below the x-axis, to give an area of -5. And then we have another bit of area above the x-axis. So what we're seeing here is that area is 5, which is what makes the integral -5. Then we're seeing that the total, now again, it's not an area that's 3. The integral from, so I'm saying this is a and b and c, the integral from a to c is 3. So that's because this negative bit of 5 has been taken away from that. So actually that means that this bit of area up here is going to be 8. So you can think about it quite a complicated way by trying to think about, oh, what's above and what's below, but actually the logic of it still holds true regardless. So there's actually a property of integrals that says, well, the integral from a to b of f of x plus the integral from b to c of f of x is equal to the integral from a to c of f of x, obviously as long as a is less than b is less than c. And that doesn't matter whether the areas are above or below the x-axis. So that's essentially what we're using here in my misleading, inaccurate diagram. It's still allowing us to think through this property. Okay, so we know that the integral from b to c of f of x is 8. That's not actually what the question asks us for. So integral from b to c of f of x is equal to 8. And so we're being asked to find the integral from b to c of 2 times f of x. And obviously that can come out there. And we know the integral of from b to c of f of x is 8. So that's essentially just 2 times 16. Sorry, 2 times 8, which is 16. As I said, having done this before, I'm skipping steps in my own mind. So part B. Question 5, consider the functions f and g. So f is a parabola, g is an exponential function. So we can sort of do this in 2 different ways, particularly given that we have our CAS. So we might talk that through in 2 different ways. So first thing obviously is thinking about what these functions look like and making sure that our composition is possible, that sort of thing. So the quadratic has intercepts at 0 and 4, if we were to factorize that. So obviously the turning point will be halfway between 0 and 4, so that's at 2. So the domain from 1 to infinity means that we're starting the function before its turning point. So hollow circle, and then we have the turning point at 2. When x equals 2, that'll be 4 minus 8, so -2, -4, and then the other x-intercept at 4. So that's essentially what we've got for f. So the range of f is -4 to infinity. And so that needs to be a subset of the domain of g, which given that the domain of g is R, it is. So then the way to think about the range of this overall function can be to think through this composition process. So essentially we start with the values 1 to infinity. We substitute them into that quadratic function. The output from that is this range from -4 to infinity. That then becomes the input for g of x. So now we can think through, okay, well, g of x is a exponential function reflected in the y-axis, but it's only going to be over this particular domain. So it's only going to go from -4 to infinity. Okay, so we're only going to have this bit of it. And so when x equals -4, y is e to the +4. And so the range of this is going to be, so that's now the range of g of f is going to be from 0 to e to the 4, inclusive of e to the 4. So it should be this. Now, obviously, the other way we could do it is actually work out the composite function. So if we think about the composite, we've thought through that it's actually possible. Sorry, we're not doing f of g, we're doing g of f. So g of f of x, and substituting the quadratic into the exponential. So it's e to the negative x squared minus 4x, which is e to the 4x minus x squared. And it's obviously over the domain of the composite is the domain of the original, so over the domain from 1 to infinity. So we can also just draw that graph. Sorry, that one later. So we can also draw the graph of e to the power of 4x minus x squared. Right, so we can readjust our window up here a bit. Right there. Okay, so we get something that looks like this. There is an asymptote at 0, so that's we've got this consistent thing reflecting that in terms of the range, the options for all of the ranges. And then it's about whether the maximum is at e cubed or e to the power of 4. So we could use our graph here, or we could do a function max over in the calculator screen. So if we go menu 6, 3 for maximum, find this maximum point. Now obviously that's not, we can't tell whether that's e cubed or e to the power of 4, but we could calculate that over here as a decimal just to see which one it is. Okay, so it's not that one. So let's assume, sorry, it's going to be e to the power of 4. Yeah. And so obviously that's a turning point, so it's inclusive of e to the power of 4, and so it's going to be option D. Okay, consider the function with domain, the inverse is whatever. Okay, so the inverse is not the domain of the inverse is not likely to be the same as the domain of the original, which is the option A, but it might be. So I'd like to know a bit more about what the original function looks like. It's a hyperbola, but it's not in that helpful format for a hyperbola. So I'm just going to get my CAS to convert that into a proper fraction so we can see that more helpful format. So I've gone to menu, 3 for algebra, 9 for fraction tools, 1 for proper fraction. Put this fraction in. So a proper fraction is a fraction where, if we talk about numerical fractions, where the numerator is smaller than the denominator. And that applies for algebraic fractions as well. It will simplify an algebraic fraction, proper fraction will simplify an algebraic fraction to make sure that the degree of the polynomial in the numerator is smaller than the degree of the polynomial in the denominator, which at the moment it isn't. And so it will do that by writing it in this format, which is really helpful for us when we're thinking about hyperbolas. So this is the same as this. So obviously this means that the range of f, is all real numbers except for -2, because it's clearly a hyperbola that's gone down by 2. And so that's going to be the domain of my inverse. That allows me to rule out A. Then I obviously need to find the inverse function. So I'm fairly quick to do that by hand. Again, or you might use your CAS to help you. So if we, sorry, try that again. If we, now given I've got it already typed in here, if I'm going to solve that, so swap x and y, equal to x, I'm going to rearrange that to make y the subject. And obviously again I've got that not as a proper fraction. So menu 3, 9, 1. Well, sorry, it's not an issue that I've got it not as a proper fraction. Again, I'm skipping steps, my apologies. So the rule we've just got here is it's the rule we see in option A, but we've already ruled out A because the domain's wrong. So that's right, but that's wrong. At option D, we see a similar format of rule, but that's not correct. And so we therefore need to see which of these are going to be correct. And so we want to convert, we want to convert it, find the inverse function. So we want to convert this into a proper fraction. So I'm not sure if we'll be okay with that y equals there. Yeah, it's okay. So 3 minus 7 on x minus x plus 2. So option B. Okay, question 7. A fair 6-sided die is repeatedly rolled. What is the minimum number of rolls required? So we're finding n. So the probability of rolling a 6 at least once is greater than 0.95. Okay, so this is a binomial situation. We have trials where the probability of rolling a 6 is the same at every trial. And there are 2 possibilities at each trial. We either roll a 6 or we don't roll a 6. So x is the number of 6s rolled. X is a binomial variable. We don't know n. That's the question the thing we're trying to find. We do know the probability of rolling a 6 is 1/6. And we know the probability, we want the probability of rolling a 6 at least once. So probability of x being greater than or equal to 1 has to be greater than 0.95. Okay, so given that I would advocate quite often that actually a trial and error method is often the quickest way to do these. And also, given that we've got multiple choice options here with only 4 options to test, it sort of gives us a starting point as to where we can test. So we want probability x is greater than or equal to 1. So lower bound is 1, upper bound is infinity. Oh, sorry, I didn't mean norm CDF. And then, sorry, let's go again. Menu 55, binom CDF. So B, number of trials, let's try 15, which is option A in the multiple choice. Probability of success is 1/6. We want probability x is greater than or equal to 1. So lower bound would be 1 and upper bound would be 15 if we're doing 15 trials. Okay, so that's not greater than 0.95. So then we can try 16 trials. Still not greater than 0.95, we're getting close. We can try 17 trials. And that's the first time it's greater than 0.95. So 17 is our answer. We could also use inverse binomial n, but I find the setup of inverse binomial n is a bit fiddly. And if you're not sure about it, I genuinely think a trial and error method is just as efficient. So to use inverse binomial n, this inequality here has to be a less than or equal to. So we need to take the opposite, the complement of x being greater than or equal to 1, which is x being less than or equal to 0. Now, I know in this binomial situation that is just x equals 0, but just in terms of the format of the information we need for inverse binomial n, I'd usually still write it this way. So if we've looked at the complement of the probability, then we're going to want that probability to be less than 0.05, perhaps less than or equal to would be the complement of that. So inverse binomial n, menu 55D. Cumulative probability is this 0.05. Probability of success is our probability of rolling a 6, which is 1/6. And then the number of successes, that's this x value here, once we've reformatted so that it's an x less than or equal to something. So that's going to be 0 in this instance. And we see that that gives us n has to be greater than or equal to 17. But as I said, getting the structure of the information correct in order to be able to use inverse binomial n is sometimes a bit more complicated than just using a trial and error method, particularly when we've got a multiple choice, so we've only got 4 options to test. Okay, question 8. Some values of the functions f and g are shown below. Okay, so we've essentially got a lot of points on each of f and g. The graph of the function h of x is equal to f of x minus g of x. Sorry, the graph of the function h of x, which is f of x minus g of x, must have an x-intercept at which of these? All right, so let's think about this information and see what we know. So h of x is f of x minus g of x. So that means h of 1 is f at 1 minus g at 1. So 0 minus 3, so negative 3. H at 2 is f at 2 minus g at 2. So 4 minus 4, so that's going to be 0. So that's an x-intercept if the y value is 0. So we learn from that h of 2 is equal to 0. And so therefore the x-intercept is 2, 0. So A. Question 9. At a Year 12 form, 45% of the students travelled to the event in a hired limousine, while the remaining 55% were driven to the event by a parent. Of the students who travelled in a hired limousine, 30% had a professional photo taken. Of the students who were driven by a parent, 60% had a professional photo taken. Given that a student had a professional photo taken, what is the probability a student travelled to the event in a hired limousine? Okay, so this is a pretty standard tree diagram kind of problem. The students either travelled in a limousine or didn't travel in a limousine. They either had a photo taken or didn't have a professional photo taken. We've got all the probabilities we need. This is 0.45, 0.55, 30% of those in the limousine had a professional photo, and 60% of those driven by their parents had their professional photo. Okay, so given that a student had a professional photo taken, so that's the condition. We have a conditional probability. It's given that P happened. What is the probability that the student travelled to the event in a hired limousine? So we want the probability that they got a limousine given, that they had a professional photo taken. So conditional probability, we need the intersection of those two things over the second of those two things. So the intersection, traveling in a limousine and having the photo taken, is that particular branch there. The probability of P, the probability I had the professional photo taken, is that branch and that branch. So we're going to need 0.45 times 0.3 over 0.45 times 0.3 plus 0.55 times 0.6. Okay, so 0.45, times 0.3, 0.135 over that same value plus 0.55 times 0.6. So that's 0.465. And so that's 135 on 465, which is 9 on 31. So option C. Now, I didn't type this whole expression into my CAS straight away because it would have given me a decimal answer, and then I would have had to work out how to match the fraction options that have been given. One way I could have avoided that would be to have typed all of this in using fractions, 45 on 100 times 3 on 10 over, etc., etc. Some of you probably have your CASs in exact mode, and therefore you would have got the exact value anyway. Personally, I prefer auto mode. And auto mode will give me a decimal answer if I give it decimals. So if I had typed this expression in, it would have given me the final answer as a decimal. And I can override that by obviously not entering decimals in the first place. You could also convert your approximate answer to a fraction, to exact value, and all those sorts of things. But it's just easier in this instance to work out this numerator and denominator separately, and then just multiply top and bottom by 1,000 so that we no longer have decimals in the fraction. Okay, question 10. Suppose a function f with domain from 0 to 5 inclusive, and its derivative with domain from 0 to 5 also inclusive, which actually I find interesting because my understanding of continuity is that a function isn't continuous at an endpoint. And so if it's not continuous at 0 or 5, then it's not differentiable at 0 or 5. So I would actually argue that the domain of the inverse is round brackets 0 to 5. Let's have a go. So continuous over the domain. If f dash at 2 is less than 0, so that is the gradient when x equals 2 is negative, and f dash at 4 is greater than 0, that is the gradient when x equals 4 is positive, which of these statements must be true? Okay, so let's think about what we know, and we don't know very much. 2, 3, 4, 5. The function is only defined over this domain. We know at 2 the gradient is negative, and at 4 the gradient is positive. Okay. Now we don't know where the curve is. That might be down here and up here. We don't know what the gradients are. It might be very steep and not very steep. So really that's all we know. Something like that happens. So if the function's continuous over the entire domain from 0 to 5, the only way to get from a negative gradient here at 2 to a positive gradient here at 4 is if we turn somewhere between those 2 points. Okay, so f is strictly decreasing between 0 and 2. Okay, so we actually don't know anything about what happens over here. So, if I continued my graph and said, oh, okay, yeah, so the function is going to look something like this, it might well, but it also might not. There's nothing that says that there isn't another point, that there isn't another turning point. So there's nothing that says that the gradient at 1 isn't perhaps negative, and therefore it would be turning again, in which case part A is not going to be correct all the time. F does not have an inverse function. Now, this is going to be true. So we've established that between 2 and 4 there has to be a turning point. And so therefore it's not a one-to-one function, and that means when we find the inverse, it won't be a function. And so B is definitely going to be correct. Let's just check the other options to make sure they're not true. F is positive on 4 to 5. Okay, so I've drawn my graph so it looks like F is going to be positive over here in this interval. But again, there's nothing to say that it's not going to turn around and be under the x-axis for some of that interval from 4 to 5. There's also nothing to say that the graph I drew originally shouldn't be down here. And so definitely we don't know that that's true. It might be true, but we don't have enough information to know that it will definitely be true. and f has a local minimum at x equals 3. Okay, so that's the assumption that the turning point that we know has to exist between 2 and 4 has to happen halfway between 2 and 4, but that's not the case at all. It could be anywhere between 2 and 4. So B. So B. Okay, question 11. 12 students sit in a classroom with 7 students in the first row and the other 5 students in the second row. 3 students are chosen randomly from the class. The probability that exactly 2 of the 3 students chosen are in the first row is. Okay, so this is a nice combinatorics problem. So we have 7 students in the first row. So from those 7 students, we want to choose 2 to be in the 3 chosen students. And therefore, from the 5 students in the second row, we only want to choose 1. Now we've chosen our 3 students. Over, we need to think about the total number of ways that 3 students could have been chosen. So there's 12 students from which we're choosing 3. So menu 5, sorry, divide, menu 5, divide. Getting that menu. Okay. Menu 5, 3 for combinations. So we want 7, choose 2, multiply by 5, choose 1, which will just be 5, over 12, choose 3. 21, 44. So B. Now, there are other ways you could think that through. So you could think through all of the different things that could happen. So we could have, our options would be the probability that someone's, what do we want? 2 students from the first row. So our options could be someone from the first row, someone from the first row, someone from the second row, or someone from the first row, someone from the second row, someone from the first row, or someone from the second row, someone from the first row, someone from the first row, and we could think through each of those probabilities. So the probability of our first choice being someone from the first row is going to be 7 out of the 12 students, so 7 first row students out of the 12 students. Then having picked a first row student, the probability of the next students from the first row is only 6 first row students left out of the 11 students remaining. And then the probability from the second row, well, there's 5 second row students still remaining out of the 10 students still remaining. Plus, then we could think about this option. So again, probability of the first student being selected being from the front row is 7 out of 12. Probability the second student being selected is from the second row. So there's 5 second row students out of the 11 remaining students. Sorry. And then there are 6 first row students remaining out of the 10 remaining students. Plus, if our first choice could be someone from the second row, there's 5 out of 12 students from the second row. Then we still have 7 students left in the first row out of the 11 remaining students and 6 out of the 10 remaining students. So essentially, if we look at each of these fractions, the numerators are all going to be 7 times 6 times 5. The denominators are all going to be 12 times 11 times 10. So that we actually just have 3 lots of 7 times 6 times 5 over 12 times 10 times 12 times 11 times 10. And that should give us the same answer we've got up there. But the combinatorics is actually a much more efficient way to go about doing it. So part B, option B, I mean. Question 12, the graph of y equals f of x is shown below. Which of the following options best represents the graph of y equals f of 2x plus 1? Okay, so we need to know a bit about the transformations happening here. So the more helpful way to write this is 2 times x plus a half. And then we can see clearly there we've got the dilation by a factor of half from the y-axis. And then we've also got over here the translation left by half. All right, so let's just take a few points and do those 2 things to it. So if we take this point here that's at 2, 1, dilate it by half from the y-axis and then translate it left by half, it's going to be there at half 1. If we think about this point up here and dilate it by half from the y-axis, it'll be about there, and translate it to the left by half, it's going to be about there. If we think about this point here, the point of inflection, dilate it by half from the y-axis, it's going to come into here, and then translate it by left to a half, it comes back to where it was at 1. And we could do that for its point. So it's going to be thinner and a bit of a translation. So point of inflection should be there. Turning point should be there. Sorry. Point of inflection there. Turning point there, and another turning point here. All right, so these are the key points here, I guess, that are useful. Should be half 1. This should be -1, 1. And we see that happening here. So again, let's just check our other options. So B, it's definitely been dilated by half, but it's moved to the left by more than required. It's gone left 1, I'd say. This one has been, these two have both been dilated by a factor of 2 from the y-axis, not half from the axis. Okay, question 13. The function f, which has domain from 0 to infinity, and it's the sum of a linear and a hyperbola, is mapped to the function g with the following sequence of transformations. Dilation by a factor of 3 from the y-axis, translation by 1 unit in the negative direction of the x-axis. The function g has a local minimum at the point with the coordinates. Okay, so we actually don't need to transform the whole function, because if all we're doing is dilating by a factor of 3 from the y-axis and translating left, again, down, apologies, negative y-axis, and translating down, that's not going to actually, the minimum value of the original function will still be the minimum value of that transformed function. So actually we can just find the minimum value of this function here. So we can just do it graphically. So if we sketch the graph of x on 2 plus 2 on x, let's just go back to the normal window. All right, we can see we've got a minimum happening here. So we could do menu 6 minimum. Some to the left, some to the right. Okay, and we can see that minimum point's at 2, 2. So we know f has local min at 2, 2. If we dilate this graph by a factor of 3 from the y-axis and translate it 1 unit down, the minimum is still going to be at the transformed version of the point 2, 2. So if we do those transformations to any point, dilation by a factor of 3 from the y-axis means we multiply the x coordinates by 3. Translation 1 unit down means we subtract 1 from the y coordinates. And so if we do that to the point 2, 2, we get to the point 6, 1. So A. Okay, question 14. Let h be the probability density function for a continuous random variable, where k is a positive real number, the value of the probability of x being less than 0.5. Okay, so we're going to need to work out k first of all. So we're going to need to use the total area. So if we integrate from -3 to 0, x on 6 plus k, and integrate from 0 to 1, negative x on 2 plus k, that should equal 1. So if we solve, shift plus for integral, x on 6, from -3 to 0, x on 6 plus k, and then plus another integral from 0 to 1, minus x on 2 plus k. Oops, solve equal to 1 for k. Okay, so k equals half. All right, so that's the y coordinates of these two lines. If you think about, so when, obviously that's when x equals 0, y is going to be k for both of them. So we know this goes through the point 0, 1 half. When x equals -3, if we put -3 in here, and this is a half, so it's -1/2 plus a half, so it's going to be 0. Same over here for the other function. The other part of the function, I should say. We know that that's when x equals 0, y will be k, so it's going to be 0, 1/2. And when x equals 1, -1/2 plus +1/2, so it's going to be 0. So we've got x-intercepts at these two endpoints. Okay, so just thinking about what our probability density function looks like. So 1, 2, 3, and 1. Going to be here at -3, 0. Going to come up here to that y-intercept to the half. The other function also has a y-intercept to the half. And down here to this x-intercept at 1. Okay, so the value, we want to find the value of the probability of x being less than 0.5. So 0.5 is over here. So rather than setting up two integrals under the two separate lines to find that area there, instead it's going to be easier to find this area here. So that area, you could use triangles, but given you've got a has integrals just as quick, is the integral from 0.5 to 1 of minus x on 2 plus a half. Okay, so 5 to 1 of negative x on 2 plus 1 on 2 dx. Okay, 0 point, let me, gave me a decimal because I put this limit of integration in as a decimal. So if I write 1/2 here instead, it will give me an exact value. Okay, so that's 1/16. And so therefore the blue area, which is what we're actually trying to find, is 1 minus 1/16. And so that's 15/16. So B. Okay, question 15. Points of inflection of the graph of All right, so let's have a look at it. We can say, you should be able to see a few things about it. Obviously, it's going to be translated up by 2. It's a reflected tan graph. Its period is going to be pi on pi, so it's going to be 1, and it's gone to the right by a quarter. All right, so we could think this through. A standard tan graph, asymptote x equals, a standard period of a tan graph looks something like this. This would be the end of the period here, so in this case that would be 1, and this would be the asymptote here, so that would be a half. Obviously we need to translate this. We need to first of all reflect this graph and then translate it it's right by a quarter and up by 2. So this point here is going to go right by a quarter and up by 2, so it's going to be here. The asymptote is going to go right by a quarter, so it's going to be over here at 3/4. So we're going to have x equals 3/4 with an asymptote. The point of inflection is going to be there at 1/4 2. Sorry. 2. So reflector shows it's going to go this way. Period is 1. So if we go 1 back from here, this other asymptote back here is going to be at x equals -1/4. So essentially that all got a bit messy, but what we have here, so what we have here, having thought that through, and again we could use our cas to help us, is we can have an asymptote at x equals -1/4 and at x equals 3/4. Halfway along from where there is where the point of inflection will be when x equals 1/4. Tan graph's going this way. It's also gone up by 2. So this is 1/4 2. And then obviously the next point of inflection is going to be 1 period along from that. And the next point of inflection is going to be 1 period along from that. So the points of inflection are all going to be at 1/4 plus k, let's say, but k is any integer. And the y value is always 2. So that looks like A. Question 16, suppose that a differentiable function f and its derivative f dash, both have domain of R, satisfy f of 4 equals 25 and f dash of 4 equals 15. Okay, so the graph goes through the point 4, 25 and has a gradient of 15 at that point. Determine the gradient of the tangent line to the graph of the square root of f of x at x equals 4. Okay, so y equals square root of x. Sorry, not square root of x. Sorry. Square root of f of x. So that is f of x to the power of a half. So dy dx is half times f of x to the power of -half. So I'm using chain rule. Multiplied by the derivative of the inside, which is f dash x. Okay, so f of x to the power of negative half is 1 on square root of f of x. So what we've got here is f dash x on 2 times the square root of f of x. Okay, so if we want when x equals 4, so we want gradient when x equals 4, so that means we're going to have f dash at 4 over 2 times the square root of f at 4, and we know both of those things. So f dash at 4 is 15 over 2 times the square root of f at 4, which is 25. So that is 15 on 2 times 5, which is, you can either cancel down the 5 and the 15, so you get 3 on 2, or you're going to get 15 on 10, which then you need to cancel down to 3 on 2. So D. Right, then we have a pseudocode. I'd be very surprised if we saw pseudocode, more than just one multiple choice on pseudocode in future exams as well. So it's really just about systematically being able to work your way through the code. This is not a code you've seen before. This is not a code you're expected to know before you arrive here, but you're just expected to be able to follow the logical sequences of the if statements and the while statements in order to be able to work your way through. So in this case, we want to know, in order, the algorithm prints the values what? Okay, so the algorithm is about printing the roots of the cubic polynomial. So that is the values where the function equals 0, so the x-intercepts. All right, so the code defines f of x, first of all, as per the question. It also defines c as being f of 0 before we even start. So f at 0 for this function is going to be 18. So that means c is going to be 18 to start with. Then we say, well, if c is less than 0, which it isn't, so we're just going to get straight to the end if, while c is bigger than 0, which it is. Okay, so as long as c is bigger than 0, we're going to continue to work our way around through this while loop as long as c is bigger than 0. If f at c equals 0, then print c, and if f at negative c equals 0, then print negative c, and if, and then we decrease the value of c by 1. Okay, so let's think about just working our way through what happens here. All right, so we have a c value. We check whether f at c equals 0. We check whether f at negative c equals 0. And then we may or may not print something. So in start with c equals 18. So that means we can go through the while loop. If f at c equals 0. Okay, so f at, I need to define f of x first of all. F of x, equals x cubed minus 2x squared minus 9x plus 18. Okay, so f at 18. Okay, definitely not 0. So we can skip over this first if statement. If f of negative c equals 0, so f at negative 18, also not 0. So we can skip over that if statement, so we're not doing any printing. We're now going to subtract 1 from c, so we get to 17. If f at 17 equals 0, nope. So we skip over that if statement. If f of negative 17 equals 0, no. So we're going to skip over that if statement, and therefore we're not going to print anything. And we're going to subtract 1 from c. Now, it feels like these numbers are very big and quite a long way off f of c equaling 0. So actually, if we think about, first of all, what solutions are we expecting the code to print? It's going to give us the x-intercepts. So let's see what the x-intercepts are. That'll at least help us to skip ahead to some values that are going to be closer. So solve f of x equals 0 for x. All right, so f of x equals 0 gives us x equals negative 3, 2, and 3. So what we want is for the output of this code to be those 3 values. The question is, in which order are we going to obtain those 3 values using this particular code? Okay, so I'm going to skip straight ahead because we can see that c equals -3 or 2 or 3 are the only things they give us. So let's stay in order. So we continue to subtract 1 from c, so the highest of those values is 3. So let's see, when x equals 3. So we're going to work out f of 3 and find that that does equal 0. So if that does equal 0, so if this is true, then we're going to print c. So we're going to print the value of 3. Then we get to the end of this if statement, and we go straight into the next if statement from there. So if f at -c equals 0, so f at -3 also equals 0. So we haven't actually gone on to our next value of c yet, that we're not to this point yet where we have to subtract 1 from c. And so then we're going to write down, we're going to print -c, so we're going to print -3. Okay, so now we've got to the end of this second if statement. So we're here. We're going to now subtract 1 from c, which is going to make it 2. And then we're going to go again. So we're going to go f at 2. Oh, that's also 0. So then we're going to print the c value. That's 2. And then we're going to go f at -c. So it'd be -2. F at -2, also not 0. And so we won't print anything from that one. Sorry, this one's true. And we can keep going, but we've actually got, if we continued on from that, then we would subtract 1 from c again, and so we would get c equals 1. We know that f of 1 is not 0, so we don't print anything there. We know that f at -1, sorry, f at -1 is 24, which is not 0. And so we don't print anything from that. And then we would subtract 1 from c again, and so we would get to 0. But the while loop is while c is greater than 0. So we're going to stop the while loop there. And that means we're going to get to the end of the code. So the output is going to be 3, -3, 2, printed in that order, and so that's D. Okay, question 18. So just 3 more multiple choice to go. Find the value of x which maximizes the area of the trapezium below. Okay, so area of a trapezium is half times the height of the trapezium times a plus b, which is the sum of the lengths of the parallel sides. So we need to think about the height of the trapezium. Now we've got a nice right-angled triangle happening here. And so we can use Pythagoras in that triangle. We know h squared plus x squared equals 10 squared. So that is h squared equals 100 minus x squared. And so h is the square root of 100 minus x squared. Okay, so the area in terms of x is going to be half times the height times the sum of the two parallel sides. So that's x plus 3x. So that's 4x, which when we times by half leaves us with 2x. Okay, so now we want the maximum area of the trapezium, so we want to maximize this function. So let's just define it. 2x times the square root of 100 minus x squared. It's done. I think we'll just use function max. We could grab that menu for function maximum is 8. We want the function maximum of a of x. I need to put comma x, I think, function max. Okay. All right, so maximum area is when x equals 5 root 2. Now the question asked us for the value of x. So if the question asked you for the maximum area, you'd then need to go on and put that value back into your area equation, and that would be the option you'd be looking for. Okay, question 19. Consider the normal random variable x that satisfies probability x less than 10 equals 0.2 and probability x greater than 18 equals 0.2. Okay, so this would be achievable using, given we don't know the mean or the standard deviation. And we know how to do that. We standardize, we use z-scores, etc. But we actually have quite helpful information here if we think graphically about what's happening here. We know the probability of x being less than 10 is 0.2. So this area here is 0.2. We also know the probability of x being greater than 18 is also 0.2. So because it's the symmetry of those areas, we therefore know straight away that the mean has to be halfway between 10 and 18. So the mean must be 14. So we know x is a normally distributed variable with a mean of 14 and an unknown standard deviation. So we're going to need to find the standard deviation first. So we're going to use one of these probability facts that we know about. Probability that x is less than 10 is equal to 0.2. So menu 3, 1, I'm going to solve a norm CDF, so menu 552. Lower bound is negative infinity, upper bound is, now it's less than, it's normal, so that's okay. Bound is 10, mean is 14, standard deviation is what we don't know. Okay, so that's what we're solving. We want that norm CDF to equal 0.2. I'm going to solve that for S. Now your CADs can only solve an equation with norm CDF in it for the standard deviation if we give it a little hint and tell it that the standard deviation has to be positive. Okay, so standard deviation is 4.75. And so then we want the probability that x is less than 12. So I'm just going to copy this value so we can use it. Okay, Control C. All right, so now it's just a straight binomial probability calculation. So menu 5B. Number of trials is 14. Probability of success. Sorry, it's not binomial, it's normal. Number of trials. Let's try that again. Menu 552, norm CDF. So lower bound negative infinity, upper bound is 12. Mean we know is 14, and we've just calculated standard deviation. So let's place that here. And so this is equal to 0.3369. So option C. Okay, then we have question 20. So f is a function, domain is I, it has an average value of k on the interval from 0 to 2 and satisfies f of x equals f of x plus 2 for all x values. The value of the definite integral from 2 to 6 of f of x is. Okay, so we've got a couple of things to use here. Average value. So we know the average value is k over the interval from 0 to 2. So average value is 1 on 2 minus 0, integral from 0 to 2 of f of x. And we know that that is equal to k. Which means half times integral from 0 to 2 of f of x is k, and so integral from 0 to 2 of f of x is 2k. Okay, so then we need to think about this and what that tells us. So that tells us that if we translate the graph to the left by 2, we still get the same graph. And so it has to be some kind of periodic function. Okay, so what we're saying here is whatever's happening here, when we translate to the left by 2, we still get the same graph again. So for example, but for all x values, and this function has a domain of R. So it must be doing something like this, where this is, it has to, whatever it is, it doesn't have to look like this. It has to be repeating though, every 2 units. So therefore, if what we know is this bit of area here is 2k, then we also know that this bit of area here is 2k, and we also know that this bit of area here is 2k. And so therefore, the integral from 2 to 6 of f of x is going to be 4k, because we're just talking about this, just talking about this bit and this bit. So C. So not too curly for a last question of the multiple choice, but you do need to be able to, again, think graphically about what does this mean, and what am I learning from that, and how can I use that? Okay, that brings us to the end of the multiple choice. Let's move on to section B. Okay, so usual instructions for section B, spaces, answer in the spaces provided, answer in English, exact value unless otherwise specified, and where a question is worth more than 1 mark, appropriate working must be shown. So you can't just write an answer. Even if there's 2 answers, I wouldn't just write an answer in a 2-mark question. I would always make sure you've written some kind of working along the way. Okay, let's clear our CAS from multiple choice. And let's get going. So consider the function. Okay, so f is potentially a quartic, depending on the value of a. So we want to, no, sorry, it is a quartic, regardless of a, but could have up to 4x intercepts, depending on the value of a. So state in terms of a, where required, the values of x for which f of x equals 0. Okay, it's a 1-mark question, so answer is fine. So from that first bracket, we're going to get x equals -1. From the second bracket, we're going to get x equals -a. From the third bracket, we're going to get x equals 2. And from the fourth bracket, we're going to get x equals 2a. So a is a real number, so a could be positive or negative. So just looking at that. Okay, find the values of a for which the graph of y equals f of x has exactly 3 x-intercepts. Okay, so regardless of what a is, there are going to be at least 2, because x equals -1 and x equals 2 are going to be x-intercepts. So therefore, we're going to get exactly 3 x-intercepts if one or other of these 2 unknown intercepts is equal to -1, or if they're equal to 2, or if they're equal to each other. So there's actually kind of quite a few different cases for us to think about. So obviously, if -a equals 2a, that means that a equals 0. That would mean that both of these intercepts are x equals 0, and so therefore we only get 3 intercepts, -1, 2, and 0. So that's one option. We also could think about if that unknown intercept at -a is equal to -1, so that would mean a equals 1. But actually, if we think about a equals 1, then our intercepts would be -1, -1, 2, and 2. So actually, we only have 2 intercepts, not 3, when a equals 1. So that one's actually not going to work. Because if we think about it, it's essentially giving us the same thing as if we did 2a equals 2, also implies a equals 1. And so a equals 1 only gives 2 intercepts. Sorry, calibration issue at the moment, I think. I need to sort it out. So we also need to think about if -a were to equal 2. So that would be a equals -2. So if we had that, our intercepts would be -1, 2, 2, and -4. So yes, we'd have 3 intercepts. Then we also need to think about if 2a equals -1. So that would be a equals -1/2. So if that happened, we would have intercepts at -1, -1/2, 2, and -1. So therefore we get another doubler. So in summary, we've got 3 possible values that would give us 3 x-intercepts. A equals 0, -2, or -1/2. So just being careful about that a equals 1 option. It actually doesn't end up giving us 3 unique intercepts. It only gives us 2. So exactly 4 intercepts, we would want them all to be different, okay? And that's going to happen if a is anything except for the values we've calculated up here, and also except for 1, because we know that only gives us 2 x-intercepts. If a is anything else, then the -a and 2a intercepts will be 2 different things, and they won't equal -1 or 2, so we'll get 4 different things. So a is an element of all real numbers, except for, now I'm going to list them in order in a set, so -2, -1/2, 0, and also 1, because 1 only gives us 2 x-intercepts. Okay, it's just a 1-marker. Okay, so again, just looking at back here in terms of this 2-marker, it depends on how the marking scheme allocated the marks. And actually now VCAA are publishing the assessment guide, so the marking scheme. But it's likely that the answer mark, a equals 0, -2, and -½ is only worth 1. And the other 1 is some sort of method mark for seeing that you're able to think about equating the different combinations of x-intercepts. So be careful about just writing down a single answer in 2 marks. Now, it's possible that in a given year, the marking scheme for this question might be 2 marks just for the answers. You might get 1 mark for getting at least 2 A values correct and 2 marks for getting 3 of them correct, and no marks, or 1 mark for if you got 4 or something like that. But you need to be careful about it. So more than 1 mark, always making sure that you're showing some working. Okay, part C. Let G be this function here, so still a quartic, so it's a particular example of f of x. It's the example of f of x where a equals 1, and we can see that we only get 2 x-intercepts when a equals 1. And so again, if you did give a equals 1 up here in B part 1, this should be a sort of prompt. So you want to be thinking about these parts of this question as being part of one big whole question. And each time you're answering a part, it's possibly feeding into information from the previous parts, using information from the previous parts, or feeding back into the previous parts. So in this instance, we can see very clearly now that we've written it out with a equals 1, that when a equals 1, f of x only has 2 solutions, or 2 x-intercepts, I should say. Okay, so find g dash x. All right, so now that we've actually got a specific function, we might define it. Sorry, it's not f, it's g. So I'm a big advocate for always using the same variables in your CAS as on the paper. It will help you to avoid using the wrong variables in what you write on your exam. So x minus 2 squared. Okay, so that's g of x. So derivative of g of x. So let's have the shift on. Derivative of g of x. So g dash x is 2 times x minus 2 times x plus 1 times 2x minus 1. Find the coordinates of the local maximum of g. All right, so it's only a 1 mark question, so we only need an answer. So we can do a function max, or we can solve derivative equal to 0 and think about all the points. But actually, for 1 mark, I'd be using function max in my CAS. So function max of g of x, actually it might give me infinity here. Yeah, okay. So actually if we think about, sorry, we should have thought about this. We should think graphically always. So this has turning points and x-intercepts at -1 and +2. We can see from the g dash x that there are turning points at -1 and +2, but also at +½ and we know that it's a positive quartic. It's going to be a nice symmetric one. So this is going to be half somewhere. This is 2, 0, and this is -1, 0. Okay, so we can actually see from thinking through our graph that the local maximum is when x equals 1/2. And so we want the coordinates. We're going to need to work out g of 1/2. So that is 81 on 16. So therefore, max at the point 1/2, 81 on 16. Make sure you give your answer as a pair of coordinates for the 1 mark. Find the values of x for which the derivative is positive. Okay, again, having thought through our graph here, we can see we have positive gradient here between these 2 stationary points and over here. So that is, so g dash x is greater than 0 for x is an element of, so -1 to 1/2, not inclusive of either, along with 2 to infinity, not inclusive of 2 or infinity, obviously. Again, just 1 mark for your answer there. So consider the 2 tangent lines to the graph of g of x at the points where x equals those 2 values. Determine the coordinates of the point of intersection of these 2 tangent lines. Okay, so let's just calculate the 2 tangents. So tangent at x equals -√3 plus 1 on 2 is going to be, so 9 for tangent line, tangent to g of x, when x is equal to -√3 2. Okay, so it is y equals 3 root 3x minus 3 times 2 root 3 minus 9 all on 4. What's your transcription of those? These are the kinds of questions where, where when they comment on transcription errors in the examiner's report, they're often talking about this sort of thing where you just copy that fraction out slightly incorrectly, you leave a bracket off, or you write a plus instead of a minus, or whatever it might be. So you really need to take care when transcribing things from your CAS. So the other tangent at root 3 plus 1 and 2, let's just go to this. So it's positive root 3 plus 1 is this. So it's y equals negative 3 root 3x. So same gradient, but the negative version, plus 3 times 2 root 3 plus 4. So same, the line intercepts? No, not quite. There's a minus 9 and a plus 9. Okay, so we found the equations of the two tangents. We're going to need the points of intersection. So we need to equate them. So we need 3 root 3 minus 3 times 2 root 3 minus 9 on 4 to be equal to, 3 root 3x minus 3 root 3x plus 3 times 2 root 3 plus 9 on 4. Okay, so in my case, I'm going to solve that equation equal to that equation for x. Get x equals a half. And then obviously we need to substitute x equals a half into one of these tangent equations. So let's take that. Let's do, given that x equals a half, and so we get 27 on 4. And so therefore our answer is 27 on 4. So that's the point where those two tangents intersect. Okay, part D. Let g remain as the same function. Okay, so remember that's f when a equals 1. Let h be the function f when a equals negative 1. Okay, so let's define a new function. Let's define h of x as x plus 1. Sure what we're going to need in our CAS actually. Let's put it in here and see where we go. At least we can look at the graphs in the CAS. X plus 2 and x minus 2. Okay, so that's got 4x intercepts, all cuts at 1, negative 1, 2, and negative 2. So this is going to look something like, it's going to cut here, cut here, cut here, cut here. Okay, but no, same dilation factor at the front, so it's actually the same shaped quartic. We're just shifting it around. You can see it's still a nice symmetric quartic, given that these are all nice symmetric intercepts. So using translations only, describe a sequence of transformations of h for which its image would have a local maximum as the same coordinates of that of g. So we need to think about the local maximum of h. So we can see that it's going to happen when x equals 0. So h of 0 is 4. So 0, 4 is the local maximum. So we need to go, so let's be clear which way we're going. Using translations only, describe a sequence of transformations of h. So we're transforming h to get it to g. Okay, so the local max for g was this one here, half 81 on 16. So we want translations that take the local max of h, which is 0, 4, to the local max of g, which is half 81 on 16. Okay, so that means we're going to need to translation to the right by half, and translation, is that up or down? 81 and 16, I think so. It's 5 point something, so we're going up. Translation up by, okay, so let's do, need to work out that minus half. Translation I done that the wrong way around? So we're saying we're going to a point which is somewhere up here. Oh, why did I subtract half? Sorry, the y value is 4. So 81 on 16. It was too big. 81 on 16 minus 4. Okay, so we're going up by 17 on 16 units. So just read very carefully the direction of the translations. Actually, the first time I did this paper, I did all these transformations in this part backwards. I went from G to H. So you're describing a sequence of transformations of H to G. Okay, so just make sure you're careful about the direction. It's only 1 mark, so you're going to need to get both of those correct. Okay, so then using a dilation and translations, describe a different sequence of transformations of H. So again, we're transforming H, for which its image would have both local minimums at the same coordinates as that of G. Okay, so we need to think about where the local minimums of H are, first of all. So let's solve the derivative of H equal to 0. So we're going to have H dash X equals 0. Oops. Okay, so we already knew there was a turning point when x equals 0. That's that local maximum, but now we know where the other two are. So it's x equals plus and minus root 10 on 2, and x equals 0, which is the one we knew about. So local minima, it's going to be negative root 10 on 2. Let's calculate what the y value is. Negative square root 10 over 2. Okay, negative 4, and also positive root 10 on 2. Imagine it has the same y value because we can see from the graph that it's symmetric. Let's just check it. Yep, negative 9 on 4. Okay, so g of x had local minima. So that's h's local minima. G's local minima they were on the x-axis. So they were at negative 1, 0 and 2, 0. And then we do also want the to have both local minimums at the same coordinates as that of G. Okay, so we need to sort of think about, there's going to be a dilation required here. So again, let's think about the graph. So let's see if we can draw them both side by side here. So we're going to have okay, so this is root 10 onto negative 9 on 4. This is negative root 10 onto negative 9 on 4. This is 0, 4. And then we want to go to this graph. That's 2, 0 and 1, 0. And this was half, again, 81, 16. Okay, so we want to use a dilation and translations. So this is to go from H, which is this one, to G, which is this one. Okay, so before we translate it away from the y-axis, it's got really nice symmetry about the y-axis at the moment. So before we translate it away from the y-axis, we want to do the dilation that makes sure that the turning points are in the right location. So what we kind of want to think about is you could do it either way, but essentially you could think about this distance from here to here, okay, is going to be 2 lots of root 10 on 2, so that's going to be root 10, that distance between the minimums, whereas here the distance between the minimums is 3. Okay, so we need to dilate it so the distance goes from being root 10 to being 3. Okay, so we need to do root 10 times some kind of dilation factor has to equal 3, and so k is going to have to be 3 on root 10, root 10, to get the dilations happening. Obviously that could also be written as 3 root 10 on 10, but don't need to rationalise. So we're definitely going to need to dilate by that factor from the y-axis so that the stationary points, the local minima, are the same distance apart. And then we need to translate them. So once we've done that, let me think about it. Yeah, so once we've done that, what should happen now is, because this distance between them is now going to be 3, this should move into being at -1/2, and this should move into being at +1/2. So that now means that there's, no, not half, sorry, 3 on 2, -3 on 2 and +3 on 2. So it should now move in. So those are at 3 on 2. -3 on 2 and +3 on 2. So we would now want those turning points not to be at -3 on 2, but to be at, sorry, that should be a -1 over there, -1. So it means moving it to the right by half. Similarly, the one that's going to be now at +3 on 2, if we move it to the right by half, it's going to be at 2. Okay, so we need to definitely go to the right by half. Let me just move that up. So that's then going to get the x-coordinates of the turning point in the right location. And then obviously we need to shift up so that those turning points are on the x-axis. So let's list out what we've got here. So we've got dilation by a factor of 3 on root 10 from the y-axis. That's going to get the distance between those local minima correct. Then we're going to need to translate right. You don't need to say in the positive direction of the x-axis. It's a real waste of time on words. Right by half units, half a unit probably, and translation up by 9 on 4 units. Okay, dilating by a factor of 3 on root 10 from the y-axis is going to make the x-coordinates of the stationary points at -3 on 2 and +3 on 2. Then we need to translate right by half to make those x-coordinates -1 and 2, and then we need to go up by 9 on 4 units. So obviously the up by 9 on 4 is the only transformation affecting the y-coordinate, so it can go in any place in your order, but the dilation by a factor of 3 on root 10 from the y-axis needs to be before the translation to the right by half units. There would be an alternative sequence of transformations that you could do which would have the dilation afterwards, but that would be a more complicated dilation to think through. So that wouldn't be the only correct answer, but that's the most obvious correct answer. Okay, so question 2. A model for the temperature in a room in degrees Celsius is given by this function here. So they're just linear. But T represents the time in hours after a heater is switched on. Express the derivative as a hybrid function. Okay, so let's have a think about whether or not they meet at 1/3. Let's think about what this looks like. So when t equals a third, so 12 plus 30 times a third, I can do that in my head. That's going to be 12 plus 10, so it's going to be 22. So they will meet. So the y-intercept of this is 12. So we essentially have something. Start here at 0, 12. When x equals a third, or t equals a third, sorry, it's up here at 1/3, 22, and then it's just y equals 22 onwards. Okay, so that's our function. So express the derivative f dash t as a hybrid function. So derivative, is going to be, so derivative of 12 plus 30t is just 30, and the derivative of 22 is just 0, but we need to think about domains here. Now, I'm going to just check the marking guide, because I suspect they possibly accepted 2 answers here, because VCAA tends to be a bit lax, or a slightly different definition to me about derivative continuity at an endpoint and hence differentiability at an endpoint. So we'll just bear with me a second. Just look at the marking guide for exam 2. So question 2. So I've got it lined up to be able to show you on the screen. So we're looking at 2A. Yes, so they did accept 2 versions. Personally, I would say that the function is not continuous at its endpoint and therefore it's not differentiable at its endpoint. And so I would say that this derivative should be this. The domain for that should be that. And then obviously the function is definitely not differentiable at t equals a third. And so t is greater than a third. But the marking guide would also have accepted this as a less than or equal to. Okay, so either of those would be correct. Personally, the way I teach about continuity and differentiability, I would argue that the function, because we don't know about the left limit, the function is not continuous at t equals 0, and so therefore it's not differentiable at t equals 0. So that would be my answer. And according to the marking guide, both would have been awarded marks. Okay, so find the average rate of change in temperature predicted by the model between t equals 0 and t equals half. Okay, so average rate of change is just gradient of a straight line. So obviously a half is somewhere past here, but average rate of change is just average gradient between these 2 points. So it's literally just a rise over run calculation. So average rate of change is quite literally f at 1/2 minus f at 0 over 1/2 minus 0. So let's define this function. When I'm working with piecewise functions, I like to define a couple of things. So let's define the piecewise function, because sometimes the CADs can do things quite neatly when we do that. So template palette over here, that's what we want. So we want 12 plus 30t, where 0 is less than or equal to t, which is less than or equal to 1/3. And then we want t equals 22, where t is greater than a third. Okay, so define that, but then it's actually also helpful to have the 2 separate parts of the piecewise function defined, the rules separately, because it's just easier to make substitutions if you need to. Now these are very simple functions, so sorry, that should be f of t, and left out the equals. So I would define as f1 and f2. Now I'm using this as an example. These are such simple functions that I probably wouldn't define them separately. It would be easy enough to substitute in separately. Okay, but we're doing f of a half, then it will work out which piece it should look at. We should be able to see that that's 22 looking at our graph. Minus f at 0, which we can see from our graph again, is 12 over a half. So that's 10 divided by a half, which is 10 times 2, so it's 20. Do we have units here? What are we dealing with? We're measuring temperature in Celsius, so this is in degrees, and we're measuring time in hours. So this is 20 degrees Celsius per hour. It actually told us that in the units were in the question. Now, interestingly, I've recently had some clarification. If the units weren't stated here, if it just said find the average rate of change, your answer would need to include the units. The fact that the stem of the question states that the answer is going to be in degrees Celsius per hour means that that's been given to us and we don't need to state that. But if it didn't actually give the units, you do actually need to give the units. And I think that's a bit of a shift in the marking policy, but something worth being aware of. Okay, so another model for the temperature in the room is given by G of T. Let's define this. So G of T is equal to 22 minus 10 E, make sure you use the proper E, to the negative 6t. Find the derivative, so shift minus with respect to t, G of t. So G dash T is 60 e to the negative 6t. Find the value of t for which G dash T equals 10. So we're going to solve that equal to 10 for t. Again, it's a 1-mark question. So derivative of t equals 10 gives t equals 1/6 log e of 6. We want 3 decimal places. So that is 0.299. Okay, find the time where t is between 0 and 1 when the temperatures predicted by the models F and G are equal. Okay, so we just want so we need to think about when G of t is equal to F of t. Now I'm going to see how my CAS will go solving the piecewise function. Let's see. Menu31 G of t equals F of t for t. Let's put that domain restriction, given that not inclusive of 0. So 0 is less than t, which is less than 1. Let's be a little bit careful about that one. So I think we should be a bit careful about what's happening there. So let's think about them separately. Let's solve G of t equals F1 of t. Let's think about G of t equals F2 of t. Okay, so it never equals the second part of it. So that means if we think about our function, I think we might look graphically at this. So which did this, and our exponential graph, what was the equation? So it was 22. So it's going to have a y-intercept at 22, isn't it? Oh no, it's going to have y-intercept at 12. It's reflected in both axes, exponential this way. It's going to have an asymptote at 22. Yeah, so it's going to go this way, an asymptote. So they actually both start at the same y value. So I don't think this little very small number that we're getting here is, I think that actually should be 0. They should definitely intersect at 0. The y-intercept of both functions is 12. If you ever think about this, G of 0 is 12 and F of 0 is also 12. So they're intersecting on the x-axis, so that we're a bit careful about me being misled by that. So actually it's t equals 0, which is not in the domain. So I think perhaps it's been confused by the domain. Let's see what happens if we take the domain out of it. Solve the piecewise one, see what it does. There you go. So actually, why have we got... Okay, so actually this time we also don't get what we expect. We get the t equals 0, but we're missing the t equals 0.26, whatever. So let's just check graphically what we've got happening here. Let's sketch the graph of... I've got up here. That's because they're defined. Okay, that's okay, we want them. Let's just make this 30. So because I defined F1 and F2, let's have it draw them both. Oh, I've really upset it because I've defined them as T. Okay, let me go back here. I'm going to need to delete these definitions. Maybe use G1 and G2 when it's G of X, but F1 and F2 is problematic. All right, so let's redefine these. Well, let's just delete those separate definitions. Okay, so menu 1, delete variable, and then we should be able to delete F1. delete, sorry, f1 of t. 0, so we delete f1 of x. Gee, I might have caused a huge problem here. I think you just do f1. I don't think it needs that bracket. There we go. Okay, let's delete f1 and let's delete f2. Good. All right, let's go back over here. Okay, so now we don't have anything here. So let's sketch f of x, which would be the piecewise function. Great, that's it. And let's sketch g of x. Okay, so definitely don't need this much. Okay, so we know they intersect at 0. We know they're going to cross at a point here, and we know that the exponential graph asymptotes to 22, so they're not going to cross again over here. So your CAS is having real trouble with this one. So you do need to really make sure you're understanding the graphs and what's happening here. So if we have a look at menu 6, intersection, the only intersection point we're interested in is this one here. Okay, so that's that 0.266. So we're solving this equation where t is an element of 0 to 1, so the t equals 0 is not relevant, and we want 2 decimal places. I'm just going to check the rounding of that. Be careful that you haven't double rounded there. So on this screen, we can check it over on our calculator. Sorry, but I'm going to do a right click, which I have to do a right click on my CAS, but you're going to click on it once and then press Control menu. So I'm going to go Attributes, and I'm going to look at more decimal places there. Okay, slow response. Let me try that again. Okay, so to 2 decimal places, it is 0.27. Okay, but see how big, I just wanted to be careful about the double rounding. So that when it was only 3 decimal places, that was showing as a 6. Just wanted to check that everything was still okay. So 0.27, correct to 2 decimal places. Okay, find the time in that same interval when the difference between the temperatures predicted by the two models is the greatest. Okay, so the difference could happen between 0 and 0.27, which would be when the exponential graph g of x is higher than the piecewise function f of x, t, sorry. Or it could be after t equals 0.27, which would be when the blue graph, which is f of t, is higher up than the red graph. So therefore, the difference is sort of a piecewise function as well. It's g of t minus f of t when t is between 0 and 0.27. And it is f of t minus g of t when t is greater than, actually given this domain, when t is between 0.27 and 1. Okay. So we need to think about those greatest differences. So maybe let's define a function. So let's do menu 1, let's define distance 1, t as being g of t minus f of t. And then let's define distance 2 as being f of t minus g of t. And let's do a function max, so 3, 4, function maximum of d1. But that's only going to be relevant, oops, where t is between 0, sorry, it's not including 0 actually, because of that domain we were given in the question. Where t is between 0 and this number up here. We did ages ago. That. just that bit though. Okay, so the maximum is when t is approximately what accuracy we want, 2 decimal places. So it's this 0.1155, so that's 0.12. And in this bit, the max is when t is, so let's do the same thing. Change that. So that's when t is less than that, less than 1. And this time we want d2 over this domain. And that happens when t is third. Okay, so we then need to work out the greatest difference. So we want to know what is the value of d1 at that 0.1155245566. Okay, that's the distance. And we also want to know distance 2 at 1/3. Oops. That's the difference. Okay, so the maximum difference is this one in the first part of the function. So max difference, which is 1.53 degrees Celsius. It doesn't actually ask us for the max difference, is when t is approximately 0.12. Again, that's just a 1-mark question. So, you know, we're only looking for that answer. So I'm not worried about setting up big functions and derivatives equal to 0 and showing me substituting values back in, etc., etc. But it does seem quite a lot of marks for 1 mark there. So yeah, you just need to be careful about if you only defined the difference as being g of t minus f of t, function max, you'd need to both think about function max and function min, because the maximum could be a negative value, and so things get a bit complicated. So I think it's easier to think about those two separate functions, but it is just a bit time consuming. Okay, so then we have part F. So the amount of power in kilowatts used by the heater after it's switched on can be modeled by this continuous function P, whose graph is shown below. The amount of energy used by the heater in kilowatt hours can be estimated by evaluating the area between the graph of y equals P of t and the t-axis. Okay, given that P of t is continuous for t greater than or equal to 0, show that A equals this. Okay, so the two functions must join, or the two branches of the same function. So function must join at 0.4. And we can work out clearly it's 0.4, 1.5. So that means that if we substitute that point into the second branch of the function, so we're going to have 0.3 plus a times e to the negative 10 times 0.4 has to equal 1.5. So that is, let's subtract the 0.3. So we're going to have a e to the negative 4 has to equal 1.2. And so that means a has to be 1.2 divided by e to the negative 4, which is just 1.2 e to the 4. So that's what being asked to show. Find how long it takes after the heater is switched on until the heater has used 0.5 kilowatt hours of energy. Okay, so I'm just thinking about whether we need the just the function, or whether we need to think integrals. So find how long it takes after the heater is switched on until the heater has used 0.5 kilowatt hours of energy. Yeah, so the kilowatt hours are about the area. So we need to work out how long it takes for the area to be 0.5. Now, obviously, if we think about, use a different color so you can see where I'm drawing. If we just think about this first part of the function here, that total area under there is going to be 0.4 times 1.5, which is more than 0.5. So therefore, if we want to use 0.5 kilowatt hours of energy, okay, we need to think about what that number there is. So therefore, we can just use a different letter. It's just a t value, so we can just use t. So therefore, if we think about that red rectangle, its area is t times 1.5, and we need that to equal 0.5. So 1.5 times t has to be equal to 0.5, and so t has to be 0.5 on 1.5, which is 5 on 15, which is a third. So therefore, it will happen after 1/3 of an hour or 20 minutes. It says give your answer in hours, so don't write the or. So again, making sure before you move on, you go back, you reread the question, you think about those sort of levels of accuracy. Okay, so find how long it takes after the heater is switched on until the heater has used 1 kilowatt hour of energy. So again, that's about the integrals. So the integral is in measured in kilowatt hours. The function itself is just measured in kilowatts. So find how long it takes after the heater is switched on until the heater has used 1 kilowatt hour of energy. So we want to work out when the area is 1, okay, but we've already thought through the fact that this yellow bit of area is 0.6, and so therefore we can now just think about the second part of the function from here to where, so that area there is 0.4. So we can just do integral from 0.4 up to some unknown t value of the second part of the function, which is this 1.2 e to the 4 times e to the negative 10t. So that area has to be 0.4. So I'm going to solve, so I'm going to shift plus. I'm going to solve the integral from, sorry, I need to solve menu 3.1. Solve integral, which goes from 0.4. Now, do I want a decimal answer? Yes, so I'm trying to put decimals in here. Otherwise, if I want an exact answer, I'd write that it's 2/5 in my case. You can use any letter, it doesn't have to be t up there, as long as that's what you're solving for. So 0.3 plus 1.2 e to the 4 times e to the negative 10t. Now we could simplify that expression, but we don't need to, there's no reason to. And that's equal 0.4, and want to solve that for t. Okay, and we get t is approximately, and we want answer in hours, correct decimal places, 1.33 hours. 2 marks, so an integral and an answer. Okay, and we're on to question 3. Okay, so there's actually been quite a bit of a jump between me recording the answer to question 2 and moving on to question 3, so apologies if there's a bit of a shift in the recording there. So question 3, the points shown on the chart below represent monthly online sales in Australia. The variable y represents the sales in millions of dollars. The variable t represents the month when the sales were made, where t equals 1 corresponds to January 2021, t equals 2 February 2021, etc. Okay, so a cubic polynomial, p, domain 0 to 12, not inclusive of 0, is most general possible cubic, can be used to model the monthly online sales in 2021. The graph of y equals p of t is shown as a dashed curve on the set of axes above. It has a local minimum at 2,2500 and a local maximum at 11,4400. Find correct to 2 decimal places the values for a, b, c, and d. Okay, so this is a pretty routine question. Sort of, a year 10 or 11 question. So we've got our polynomials already defined for us, so we don't need to do that ourselves. We're going to need 4 equations because we've got 4 unknowns, and our 4 equations are related to the location of the 2 points and the fact that they are stationary points. So we know that p of 2 is equal to 2,500. That's it, the graph goes through the point 2 to 2,500. We also know that P of 11 is 4,400. We also know that P dash at 2, the derivative at 2 is 0 because it's a local minimum, and P dash at 11 is 0 because it's a local maximum. Okay, so let's set up the CAS to solve that. So menu 1-1, let's define our general polynomial first. P of t equals a times t cubed plus b times t squared plus c times t plus d. Okay, and simultaneous equations to solve. Now, because we want to use the derivative, it's complicated to substitute the values into the derivative in the CAS. It's messy, and it's even more messy trying to do that in a simultaneous equation. So I always define the derivative function as well. So I'm going to I'll define that as dp for derivative of p of t, and that's going to equal shift minus the derivative of p of t. Okay, and then now we can solve, so we've got simultaneous equations, menu 371. We have 4 equations, 4 unknowns will be A, B, C, and D. First equation, P of 2 equals 2,500. Yep. P of 2 equals 2,500. P of 11 equals 4,400. And then we want derivative of P at 2. So that would be much more complicated to enter in if we hadn't defined a derivative function, because you can't just do ddx of P of 2 because P of 2 is a number and the derivative of that 0. So you need to do ddx of P of x given that x equals 2. And that all gets a little bit ugly. Derivative of P at 11 is also 0. Right, so it's gives nice fractional answers, but we want correct to 2 decimal places. So Control Enter, we're going to get A is approximately negative 5.21. B is approximately 101.65. C is approximately, let's look, negative 344.03, and D is approximately 2,823.8. Okay, our answer. All right, let Q with a domain from 12 to 24. So we're now looking at, we want to look at this next year from 12 to 24. Okay. And so in this part, we want to do that by transforming our polynomial P of t. So we want to somehow translate this across and up to give us the model for, across and down, whatever it might be, to give us the model for what's happening over here. Okay, so Q is a translation of P of t. So we're going to translate P, which can be used to model the monthly online sales in 2022. So the first 12 months was 2021. This will now give us 2022. Find the values for H and K such that the graph of Q of T has a local maximum at 23,450. Okay, so P of T had a local maximum at 11,400. So that means the translations that we need to do need to move the local maximum that is currently at 11,400 so that it becomes 23,450. Okay, so that means we need to go to the right by 12 and up by 350. And so that means H is going to have to be 12. So we go right 12 and up 350. And so therefore that means H is going to be 12 and K is going to be 350. Okay, another function f can be used to model the monthly online sales. So this time it's a sort of complicated trig function. We've got part of the graph shown here. We've got the graph from 0 to 24, so the first 2 years worth, but it has a domain from 0 to 36. Complete the graph. Okay, so let's define a function here. Let's define this function so we've got it. Sorry. Menu 1, 3,000. Let's call it something. f of t equals 3000 plus 30t plus 700 cos pi t 6. It's 400 times cos pi t on 3. Alright, so obviously let's just get our cows to work out some points for us. So we want to draw it up until 36, so that endpoint is going to be important, and the question does specify label the endpoint at t equals 36 with its coordinates. So f of 36, 5,180. Okay, so looking at our scale here, so each little box represents 500. So this is about 5,200. So we want to think about sort of putting it 2/5 of the way up this box. So that's where that's going to be. 36, 5,180. All right, now let's plot out a couple other points. So we might think about the turning points. Just make sure they end up in the right place. So that we solve the derivative zero for t, but them in the domain from 24 to 36. So we get 24.04. So let's work out f of 24.04. So that's 4,820. So about 4,800. Okay, sorry, so that's where it starts. Sorry, we knew that. That's where it's going to join onto the graph. So f of 27.78. It's about 3,300. So about 27.8. Okay, so each of these is 2, so just thinking about scale there. So 27 is going to be here, and 27.8 is going to be pretty close to here. We want that to be at about 3,300. So there's 3,000, 3,500. So let's go round about here. Let's do f of, sorry. Let's go back up here, so scroll across so we can see these other values. Let's do f of 30.12. Okay, so it's about, let's say 30, a little bit past 30 and 3,600. 600. So maybe sort of about here. And then f of, this is quite fiddly really. I love this as a question, it's a bit general maths. 3,409, so about 32, 3,400. 32, 3,400, so back under here, but not as low as that other stationary point. All right, so it's going to come down, it's going to turn at that point, it's going to turn at that point, it's going to turn at this point. And then whilst 36 isn't exactly a turning point, the turning point, as we've seen, the turning point over here was just past 24. So it is going to be heading into being a turning point. So your graph should be curving back that way. Try that again, it's not very good shape. Okay. So something along those lines, I think the endpoint being accurately located and labelled with coordinates is going to be important, and then I mentioned something about shape. Okay, so part 2, the function f predicts that every 12 months, monthly online sales increase by N million dollars. Okay, so what we're seeing is, what we're kind of looking at is if we go on by 12 months, what was the increase in sales? If we go on by 12 months, what was the increase in sales? So if we do F at 12, F at 12 minus F at 0, 360, let's just check that it's the same in the next year. F at 24 minus F at 12. Oops. Yeah. Okay, so this is F at 12 minus F at 0, same as F at 24 minus F at 12, gives us 360. So that means it's $360 million. Now it does specify the units in the question, and so just around 360 would be enough to get the answer there. Find the derivative. Let's get our to do that for us. Okay, so f dash of t. Kaz always writes those big ugly fractions. You've got fractions in the sine and cos functions, and then the whole thing in a big fraction. Just write that fraction. It's just negative 400 pi on 3. Let's just write that out. Let's not put the sign in the fraction. And then it's sine of pi t on 3. Just a bit less unwieldy to write down. You're not going to end up with a tiny fraction in a fraction where your numbers then become difficult to read. Handwriting's becoming a bigger and bigger issue, we're saying, in exams. It's really important that you take the time to take care with what you write so that someone else can read it. All right, so there's our derivative. Hence meaning using the derivative. Find the maximum instantaneous rate of change for the function f, correct to the nearest $1 million per month, and the values of t in the interval. Now, technically, second derivative isn't in the maths methods course, and it annoys me that they continue to ask these questions. So I like to frame it in a way that isn't talking about the second derivative, and instead talking about it as the max min problem. So we are trying to maximize the rate of change. So we're trying to maximize gradient. So therefore, we need an equation for gradient or equation for rate of change, and that is going to be the derivative. So, so we know rate of change. I'm going to call that. That a new function. We're going to call that r of t, and that is f dash of t. And then we know to maximize a quantity, we solve the derivative equal to 0, derivative of that equal to 0. Now, in this instance, I think we're going to find this is a pretty unwieldy, a pretty unwieldy function to be dealing with. There's a lot of stationary points. So let me just define t as being the derivative here. If I were to solve the derivative of r of t equal to 0, sorry. Yep. Let's make that equal to 0 for t. Now we want 0 to 36. We're going to get a lot of stationary points, and then we have to work out which one's the maximum and da, da, da. So I think you'll find that this is not going to be the most helpful way to do it. Sorry. Less than t, which is 36. All right, and even if you control enter, I've got 1, 2, 3. It's gone too far. They've got heaps and heaps of solutions. So rather than actually solve derivative equal to 0, I'm going to use function max instead. I might still write that I'm solving derivative equal to 0. And then we're going to get t is. So instead, if we use menu for 8, because then it's only going to give us those solutions that give maximums, not minimums. So our function max of our rate function, comma t, and then again we want that domain, given that 0, I need to put domains in, it's very fiddly, plus equal to 36. Sorry, control enter. We want our answers to 1 decimal place. Okay, so now we get only 3 of those solutions, whereas there was probably 6, 7, 8 solutions before solving derivative equal to 0, and then we would have to work out which ones are maximums and which ones are minimums. So t is approximately 10.2, or 1 decimal place, 22.2, and 34. 2 also. I'm just going to note that these are the solutions for the maximum, because they're not actually all the solutions to the equation I wrote down, which is derivative equal to 0. Okay, now the question actually asks us for the instantaneous rate of change, the maximum instantaneous rate of change. So we now want to work out what that is. So we want to know max rate of change is going to be r at any one of these values. Okay, so let's do r out. I'm going to type this one. Can't see that first one, so I'll type in the second one. Sorry. All right, let's try again. R of 10 point, I always type in as much as I can for as much accuracy as I can, or copy it down if I can, but it would be messy to copy here with 3 solutions in one line. 69931. Right, so that is, we want maximum rate, instantaneous rate of change correct to the nearest $1 million, and the values of t 1 decimal place. So that's just going to be 725 million. Again, I think the question says nearest millions of dollars per month, and so I think that just writing 725 without the units would be fine. Exam 2 seemed to be a bit less worried about units than exam 1. Which is interesting. I think now that they've put out the marking guides, I think there's going to need to be some bit greater alignment between the 2 exams, just so that there are some more consistent expectations of students. I think up until this point, they've been able to mark the 2 papers fairly independently and make their own decisions about what to award marks for and what not to. But I think across the one subject, they're going to have to look to be a bit more consistent. Okay, so question 4. So we get to the probability question. Okay, so we've got airport luggage is weighed before it's checked in. The mass of each piece of luggage in kilograms is modeled by a continuous random variable x, whose probability density function is this. Okay, I'm just going to define that before we do anything else. Let's define f of x. Given that it's 0 elsewhere, I don't need to define it as a piecewise function. We can just define the part that's not 0. So 1 on 67500 times x squared times 30 minus x. Okay, a piece of luggage is labelled as heavy if its mass exceeds 23 kilograms. Write a definite interval which gives the probability that the piece of luggage is labelled as heavy. Okay, so the probability of a piece of luggage being labelled as heavy, it will happen if its mass exceeds 23 kilograms, so that's probability x is greater than 23. And so therefore, as an integral, that's going to mean integrating from 23 up to 30, which is the upper limit of the function, f of t dt. Sorry, f of x dx. So used to t's from the last question. No need to write out the expression. If the function's defined in question, you can simply refer to it as f of x. It avoids transcription errors, time, just saves time, etc., etc. Okay, find the mean of x. So the expected value of x is going to be the integral over the total domain 0 to 30 of x times f of x. So shift plus 0 to 30 x times f of x dx. So 18, the 18 kilograms. Find the standard deviation of x. Okay, so for standard deviation, we need expected value of x squared. So that's integral from 0 to 30 of x squared times f of x. Let's just edit this calculation. Oops. So that's 360. Variance of x is expected value of x squared minus expected value of x all squared. So in this case, that's 360 minus 18 squared. So 36. And standard deviation of x is square root of variance of x. So square root of 36, so 6. Given that the mass of a piece of luggage is more than the mean, find the probability it's labelled as heavy. So we want probability, so heavy was greater than 23. So we want probability the mass is greater than 23 given that the mass is greater than 18. So that means the intersection of those two things. So if something has to be both greater than 23 and greater than 18, it has to be greater than 23 over the probability x is greater than 18. Right, so it's going to require two integrals. Integral from 23 to 30 of f of x dx over integral from 18 to 30 of f of x dx. So 23 to 30 of x and 18 to 30 63161 over 27 4 zeros divided by 328 over 625. We want the answer to 3 decimal places, so it's going to be that fraction divided by this fraction to be exactly that, or 3 decimal places 0.446. So we're going to use the following information to answer parts C and D of this question. So of the travellers flying from the airport, 10% do not check any luggage, 40% check in exactly one piece of luggage, and 50% check in exactly two pieces of luggage. Assume that the mass of each piece of luggage is independent of the number of pieces checked by each traveller. Use the value of 0.234 for the probability that a piece of luggage is labelled as heavy. Let W be the discrete random variable that represents the number of pieces of luggage labelled as heavy checked in by each traveller. Okay, so we have to think about, so we want the probability, show that probability of W equaling 2 is 0.027. So what we have to think about is, so that means the probability, W is the number of pieces of heavy luggage checked in. So we want the probability that a traveller checked in two heavy pieces of luggage. So to do that, they have to have first checked in two pieces of luggage. So only 50% of people checked in two pieces of luggage. And then both of those pieces of luggage have to be heavy. So probability W equals 2 is going to be 50% of people check in two pieces. And then the probability that the first piece is heavy will be 0.234. And the probability the second piece is heavy will also be 0.234. And if we do that, we should find that we get approximately 0.027, correct to 3 decimal places. Complete the table below for the probability distribution W, correct to 3 decimal places. Okay, so I sort of thought through a tree diagram in the last question without actually drawing out the tree diagram, but it may be helpful for you to think through the tree diagram of what's happening here. So we have a passenger could have no luggage, and therefore none of the pieces of luggage are going to be heavy. A passenger could have one luggage, or a passenger could have two pieces of luggage. And that happens 10% have no luggage, 40% have one luggage, and 50% have two. Okay, and then the one luggage person, that bag could be heavy or not heavy. So that's 0.234, and then 1 minus 0.234, sorry, it's 0.766. Sorry, that should be not heavy. And then the two luggage people could have heavy or not heavy, and then they could have heavy or not heavy. So 0.234, 0.234, 0.234, 0.766, 0.766, 0.766. Okay, so we already know the probability of W equaling 2 is 0.27. So that's the probability that a traveller checks in two heavy bags. Now, if we want the probability that the traveller checks in no heavy bags, okay, so that's going to be they check in no bags at all, or they check in one piece of luggage, but it's not heavy. Okay, so the calculation for this is going to be 0.1 plus 0.4 me to change pen color, going to be 0.1 plus 0.4 times 0.766. All right, so, or actually, sorry, they could also check in 2 bags and neither of them could be heavy. So 2 bags and not heavy, not heavy. So 0.5 times 0.766 times 0.766. So that's going to be the probability of non-heavy bags. So we have 0.1 plus 0.4 times 0.766 plus 0.5 times 0.766 squared. All right, that's 69978, and we want these to 3 decimal places. So that decimal to 3 decimal places is 0.700. Still write the zeros. It's not exactly 0.7. It rounds to 0.700 if I'm asked to give it to 3 decimal places. Okay, so then I can take my 0.027. Sorry, I can take my 1 and subtract 0.027, which was this one, and subtract 0.700, which is this one, and that gives me 0.273, which even after the rounding, that all still adds up to 1. Okay, so then part D, on a particular day, a random sample of 35 pieces of luggage was selected at the airport. Let P hat be the random variable that represents the proportion of luggage labelled as heavy in random samples of 35. Okay, so this is actually a different variable. It's still sort of number of heavy pieces of luggage, but it's not number of heavy pieces of luggage checked in by a traveller. The 10%, 40%, 50% don't matter anymore. So I'm going to use a different letter here. Let's let Y be the number of pieces of heavy luggage. Okay, so Y is a binomial variable. P hat can't be binomial, but Y can be. So the proportion of can't be binomial, but the number of can be. So it's binomial where N is 35, we're checking 35 pieces of luggage, and the probability of that piece of luggage being heavy is 0.234. Now we have this connection between, we know that P hat, the proportion of pieces of heavy luggage is the number of pieces of heavy luggage divided by 35, which means that Y equals 35 times P hat. Now the question is asking us for the probability of P hat being greater than 0.2, which means we want to change that to be about Y. So 0.2 times 35, that's the probability of Y being greater than 7. Now binomial variable is discrete, so greater than 7 means 8 or more. So that's the probability that Y is greater than or equal to 8. All right, so menu 55B for binomial. N is 35, P is 0.234, lower bound is 8, upper bound is 35. Okay, so we have what we want, 3 decimal places, 0.595. Determine the probability that P hat lies within 1 standard deviation of its mean, correct to 3 decimal places. Do not use a normal approximation. Okay, so we can work out the mean of P hat, which is just P, which is in this case 0.234. We can work out the standard deviation of P hat, which is square root of P times 1 minus P over N. These formulas are on your formula sheet. So that is the square root of 0.234 times 0.766 over 35. So square root of 0.234 times 0.766 over 35. So 0.072. Okay, so we want within 1 standard deviation of the mean. So the mean minus 1 standard deviation. So my mean was 0.234 minus 1 of my standard deviations is 0.1624, and the mean plus, standard deviation. Mean plus a standard deviation, just get this, is 0.3056. Okay, so we want the probability that 0.1624 is less than p hat, which is less than 0.3056. So I'm just checking probably it lies within 1 standard deviation. Okay, good. Okay, so now I want to change that to be about my binomial variable y. So I'm going to be multiplying these two values by 35. Change from p hat to y. Okay, so that is the probability that y is between 5.69 and 10.69. Okay, so if y has to be greater than 5.69 and it's discrete, so it has to be an integer, then it can be equal to greater than or equal to 6. And if y has to be less than 10.69, it has to be an integer, that means it's less than or equal to 10. So now we can do our binomial CDF, menu 55B, chance is 35, probability of success 0.234, lower bound is 6, and upper bound is, lower bound is 6, and upper bound is 10. Okay, so that is, what accuracy do we want? 3 decimal places, 0.684. In one random sample of 50 pieces of luggage, 10 are labelled as heavy. Use this sample to find an approximate 95% confidence interval. Okay, so this is a straightforward CAS question. So menu 665 for your confidence interval. My number of successes is 10 in a sample of 50, and I want 0.9 level of confidence. And so my confidence interval is 0.106 accuracy. So it's 107. To 0.232937. A second random sample of 50 pieces of luggage is selected. Using this sample, the approximate 90% confidence interval for P is wider than the one obtained above. State the minimum and maximum number of pieces of luggage labelled as heavy in the second sample. Okay, so if we have a think about, let's just see if we made there'd be 11 heavy bags in the sample of 50, then the confidence interval is 1.23 to 0.316. So margin of error is the key thing there. So margin of error is 0.096. In the previous one, it was 0.093. So the confidence interval got wider when I have 11 pieces of heavy luggage. So I know it's going to have to be more than 10. So it's going to have to be 11. I was just checking that it got wider as I made the number of successes bigger rather than smaller. So it's definitely going to be, the interval is going to be bigger than 90%. So what we could do is think about the existing margin of error. Sorry, where am I here? So the original margin of error there is 0.93. Now, if I get that, let me get that exactly so that I can work it out. So a 90% confidence interval, I'm just working out the Z score for a 90% confidence interval. So menu 553. So if I want to be 90% confident, so I want 0.95 for my Z score. Okay, so that's my number outside the square root in the margin of error. So the margin of error is going to be, sorry, no, it's not those values, is it? It's the 10 on 50 and 40 on 50, so 1/5 times 4/5. It's not. Just realised I used 35, whereas this sample in this question is 50. Okay, so that's the margin of error. I just wanted to have that number that I could work with it. So we want, if we want the confidence interval to be wider, we want the margin of error to be bigger. So our question is asking us, what does, how many pieces of heavy luggage would there need to be? So if we think about margin of error, for a 90% confidence interval, as I said, it's 1.64. I'll use that nice and exactly in my CAS. We don't know what this p hat value is because we don't know the number of pieces of heavy luggage. That's kind of what we want to work out. We do know it's still going to be another sample of 50. We want that to be bigger than our original margin of error, which was 0.093. So if we get our cats to solve that, so let's solve, get that value there, times square root of, call it p hat in my, p is already defined. Let's use another letter, a. Solve that for a. Okay, so that means that I've just learnt that p hat is going to have to be between 0.2 and 0.8, which means if I times those things by 50, I can do it like this. Okay, so 0.2 times 50 and 0.8 times 50. So that means somewhere between p hat has to be somewhere between, sorry, not p hat. It means number of successes. So number of heavy bags. Has to be somewhere between 10 and 40. And so therefore that means that the minimum is going to be 11 heavy bags. And the maximum is going to be 39 heavy bags. And we already saw that when I made the number of successes 11, that the confidence interval did get wider. We could check, so the margin of error got bigger. That's how we looked at it. We could check, sorry. We could check that when the number of heavy bags is 39, that is still bigger than the original margin of error of 0.93. But let's have a look at what happens when we make it 40. But it goes back to being 0.93. I think you'd find that's actually exactly the same as what happens if you have 10 pieces of heavy luggage. So that doesn't make the confidence interval wider, it just makes it the same. And so therefore for it to be wider, it has to be a maximum of 39. Imagine if we made the number of heavy bags 41, we would see it drop under. Yeah, 0.89. Okay, question 4. The graph below shows the compositions of GOF and FOG, where f of x is sine x and g of x is sine 2x. Okay, so let's define some functions here. Let's define f of x equals sine x. Let's define g of x equals sine 2x. Let's define f of g as being f of g. And let's define g of f as being g of f. Right, so we have everything we need. So we've got the two graphs of GOF and FOG shown below. The graph of g of f of x has a local maximum whose x value lies in the interval 0 to 2 pi. So we're looking at this one here. Find the coordinates of the local maximum correct to one decimal place. Okay, so let's see what happens. If we do, we could solve derivative of GOF equals 0 for x. We could do that over the interval. Okay, so it doesn't like that. It gives us a general solution. Maybe we have a look graphically at what's happening here. G of f do some window adjusting here. Sort of make it a bit more close to that one. Let's do minus 12. Let's do 2 pi plus pi on 12. Just don't like to have the window right on the ends of the graph. And then let's go with sine functions, so let's go with that. Okay, so let's see. That wasn't what I meant to change, sorry. Okay, so let me just see graphically. Let's get a decimal approximation for it. Oh, we only want a decimal anyway. 1 decimal place. Okay, so let's do it graphically. The equation didn't give me a good one. So I want max, I'm going to go left to right. We want 1 decimal place. So let's just check that. Let's just check that. What I'm trying to do is try it with my mouse rather than my pen. Bring up that extra window. Right, this is what I want. Just checking that if I make the accuracy of that number bigger, it doesn't give me decimals, so it doesn't, it's exactly 1, the y value. Okay, so coordinates of this point correct to 1 decimal place. The x coordinate is 0.9 and the y coordinate is 1. State the range of GOF. Okay, so we could also find the minimum points. So, in fact, I'm going to just check that the other maximum point is at the same y value. Yes, that looks right. And then 6 minimum. So that looks to be -1. 6. Let's just check the other ones, not any lower down. Yeah, okay. So the maximum value is clearly 1 and the minimum value is clearly -1. And so therefore the range of GOF is from -1 to 1. Okay, find the derivative of f of g. Okay, so shift minus with respect to x of f of g of x. So it is f of g derivative of x with respect to x, sorry. And it's 2 cos 2x times cos sine 2x, which is just a simple chain if you think about it, doing it by hand. Show that the equation of cos of sine 2x equals 0 has no real solutions. Okay, so cos of sine 2x equals 0. So cos equals 0, x coordinate 0 at plus or minus pi on 2. So that would mean this would only be possible if the thing inside the cos equals -3 pi on 2, or -pi on 2, or pi on 2, or 3 pi on 2, etc. And as decimals, these are -4.71, -1.57, 1.57, 4.71, etc. Okay, so one of the problems is that sine of 2x has to equal something between -1 and 1. And none of these values are between -1 and 1. Okay, so what we know is sine 2x is somewhere between -1 and 1. Since none of the solutions for sine 2x lie in the range -1 to 1, there is no solution to the equation. So first, there's no solution to the equation sine of 2x equals some multiple of pi on 2. Some odd multiple of pi on 2, and therefore there can't be any solution to the equation cos of sine 2x equals 0. Find the x values of the stationary points of f of g. Okay, so if we think about solving our derivative equal to 0, so if you solve this equal to 0 in your CAS, I don't think it likes it. So menu 1, menu 3, if I solve my derivative equal to 0 for x over, obviously it's a trig function, so we need domain, over the domain from 0 to 2 pi. We need domain if we want specific solutions. Okay, so it still gives me that as a general solution. So this is where actually what it asked you to do in part 2 was about helping you. So if f of g of x equals 0, then that means that, I'm looking up here, this equation has to equal 0. Now we've already established that this bit in part 2 cannot equal 0. And so therefore, solving the derivative equal to 0 is essentially us saying you can just solve, so what I'm saying, so it equals 2 cos 2x times cos sine 2x equal to 0, which means that the only way for that to equal 0, because we've just shown that cos of sine 2x can't equal 0, is if this bit equals 0. So rather than solve derivative equal to 0, which it seemed to have some trouble with, let's just solve, trouble writing the CAS accurately today, 2 times cos of 2x. Lost a bracket somewhere. I added a bracket. There we go. So I tried to edit that one. Okay, so that's the equation. Yeah, okay, I think that's it. All right, and so when we do that, we get our solutions. X equals pi on 4, 3 pi on 4, 5 pi on 4, 7 pi on 4. Find the range of fog. Okay, let's have a quick look at fog. F of g. Okay, so it's pretty straightforward. We've just found those 4 stationary points, which we can see. I could do menu 6, 2 for minimum, 6 for maximum. Okay, so it's not giving me exact values, but it is telling me that the y value is the same at both of those stationary points. And so I can see that the maximum is at pi on 4. Work that out. Exactly, just that's for decimal. Do that in a second. And we can see that the minimum is at 3 pi on 4. Or the max is also at 5 pi on 4 and the minimum is also at 7 pi on 4. So we can work out f of g of at pi on 4, and we can work out f of g at 3 pi 4. Okay, so this is sine of 1 and this is negative sine of 1. And so therefore the range of fog is from negative sine to sine. Oops, square bracket. Okay, write a single definite integral that gives the area bounded by the graphs of f of g of x and g of f of x in the interval. Okay, so just going to delete all that just to get rid of all those points so it's not so messy. Okay, let's draw f of g and let's draw g of f. Okay, so we can see from the graphs that we had drawn back here where they were both drawn, they clearly both intersect at pi. So if we want the area bounded between them, we're looking for this bit of area here and also this bit of area here. Now, the key with this question is it asks me for a single definite integral. So whilst I could set up the integral from 0 to pi of goff minus fog and then plus the integral from pi to 2 pi of fog minus goff, it asks for a single integral. And so what I need to be able to recognise is that there's some symmetry here and these two shapes are actually equal. And so I can use a single integral just by doubling one of these integrals. So we're going to have that the area is two lots of the integral from 0 to pi of g of f of x minus f of g of x. Now, obviously, you could double the integral from pi to 2 pi, which would be f of g of x minus g of f of x. But either way, you need just a single integral. Okay, hence state the area. So now we actually want to calculate it. So we're going to have 2 times shift plus 0 which way around? Goff minus fog. So you'll notice I've literally used goff and fog as the names of the functions. And it just helps me. It means I don't have to constantly thinking about, oh, did I call goff d of x or h of x or what did I call it? The more you can use the same variables in your CAS as what's on the paper, the less issues you're going to have with accidentally writing down the wrong variable, with mixing up your functions, etc. So it's just about sort of good CAS use. All right, so we want this to two decimal places. So this interval gives us 4.97 square units. Okay, let f1 be the function sine x. I don't think that's a change of the rule, was it? F of x was sine x, but we've now just restricted its domain. So we're only looking at 0 to 2 pi, not inclusive. Find all values of x in the interval 0 to 2 pi for which the composition f1 of g is defined. Okay, so if we want f1 of g of x to be defined, we need the range of g to be a subset of the domain of f1. Okay, so range of g at the moment is -1 to 1. Okay, it's just sine of 2x. And the domain of f1 is 0 to 2 pi. Okay, so if we need this to be a subset of this, 1 is less than 2 pi, so that's not an issue. But this means that we need the range of g to only go from 0 to 1. Okay, so we need to think about g. So g of x is sine of 2x. So that means it's a sine graph with a period of pi. Okay, but we need that to only have a range from 0 to 1. So this is 1 up here. See, this is -1 down here. So we only want, these bits here, not inclusive of those points on the x-axis. So we only want this bit and this bit. Okay, so that means if we think about that, so that's obviously pi on 2, that's going to be 3 pi on 2. So therefore, it's going to be x is an element of 0 to pi on 2 in union with pi to 3 pi on 2. And that's the end of the exam. To be honest, I think a composition domain arrange question as the final question on exam 2 seemed a bit straightforward, but there were certainly some more complicated questions earlier on.